Hi students. Okay, in this video we're going to be studying the law of refraction, which is not quite the same as the law of reflection. The law of reflection states what happens when rays of light, described in the last video, bounce off of things, and the law of refraction describes what happens when they are transmitted into things. So if we take an object, we can now have three different things that can happen to a ray of light. So let's take a look at a little block of material here. And when we have a ray of light come into our material, we'll take a little red ray of light here. Let me do that at an angle. There are three things that can happen. It can either be reflected, or it can be transmitted, or it can be absorbed, in which case it's no longer light. It just becomes other forms of energy in the material. So so we're really going to be focusing on, we've focused on reflection, we're now going to be focused on transmission and the law of transmission, which is, or reflection, transmission, refraction, which is Snell's law. It actually is, I think, is Snellius law, but that's a really silly name. So we always refer to it as Snell's law. Okay, so Snell's law is mathematically very simple, but we want to look at the results of it. Remember, the law of reflection stated that the incident theta was equal to the reflected theta. In Snell's law, we have two thetas as well, and in this case, we're interested not in just theta, but we're interested in the sine of theta. Okay. Not only that, but you may remember from a previous video, we studied the material property, the index of refraction. So hopefully this term called your memory back to that particular material property. It's the same one, so it has an effect on the speed of light in a material like last week, and it has also an effect on the angle of a ray of light in a material. So we're interested in the index of refraction of a material, and we're interested in the sine of the angle of that ray of light. Okay, it's very simple once you get this down. If we choose for one material, we'll call it material 1, an array that is encountering the surface of that material at theta 1, it will always be equal to the same ray on the other side of that interface, index of refraction of the new material times the angle in the new material. Okay, let's take a look at what that looks like in this particular circumstance. So we're going to take our ray of light, and I'm going to bring it in at, I'm going to bring it in at a little bit of a tighter angle this time. Okay. Not a tighter angle, I guess a wider angle is what I mean. Now every time we have a ray of light hitting a surface, you do the same thing that you did in the mirror section of this chapter. You're going to be looking at the normal to the surface. That is always going to be your go-to. Every time a ray of light hits a surface, always draw the normal to the surface. Trust me on this. It will, especially in Snell's law, this will become very important. So we draw the normal to the surface, and then we can draw the angle that we can call, if you want, theta 1. And then we have the ray of light after it strikes the material is going to be not continuing in a straight line. It will be bent. Now, the way that you can always determine what the angle is that it's going to be bent is you look at your materials and you say, okay, this particular ray is coming in at, what did we have here, 36 degrees. degrees, okay? So theta 1 is 36 degrees here. And let's go ahead and write that out. We're going to say theta 1 is equal to 36 degrees. And we know that, let's say this material outside is just air. So we know that the index of refraction for the material outside is equal to 1 within 3 significant digits. If we keep going with our decimals, we'll find some extra bits here, but air and vacuum have pretty much the same index of refraction within this precision. So we've got information about our first material. Then we look at our second material and say, well, what is that material? Let's say it's glass. So N2 is glass and therefore has an index of refraction of different indices of refraction. I'm going to go ahead and give that one 1.55 for this particular type of glass. Okay, so let's label this glass, and this is air. Now let's look at our ray, find out what happens. This is the direction it was originally going. The angle theta here, the size of that angle visually in this diagram, the size of that angle should be wide in comparison to the angle here on the inside. And the reason is because this is a less dense material and glass is a more dense material and therefore has a higher index of refraction. So just intuitively, that gives you the idea that we know that this is going to collapse closer to the normal, not farther away from the normal. Because glass is a more dense material, we can therefore make sure that the ray is closer to the normal. More dense, closer to the normal, less dense, farther away from the normal. Okay. This gives us a new angle, theta 2. If you prefer, you can always refer to this as theta air and then the next one as theta glass. So that's one way to make sure that you don't mix up your 1s and 2s. So we want to know what is theta 2. We don't know. As a matter of fact, we can calculate this, and I really shouldn't have drawn that until we calculated that. Let me get rid of that, and we're going to come back and I just wanted you to get a sense of what direction it's going to go. But theta 2, we want to know what that is. That's always going to cross the normal also. It's never going to come on this side of the normal. It's always going to cross the normal inside the material. So it's never going to be on this side. It's always going to be on that side. Let's calculate that according to Snell's law here. Snell's law dictates that N1, which is 1, times sine theta 1, which is sine of, make sure your calculator is in degree mode, 36 degrees, sine of 36 degrees. Okay, so that's our first two, and those are going to be equal to the second two. The index of refraction of 1.55 times the sine of angle 2. The biggest problem that I see people run into here is that they switch the indices of refraction on here on accident just because they're not paying attention. So be careful about that. Alright, so this leads us to sine of theta 2 is equal to, we would have 1 over 1.55 times sine of 36 degrees, and that should give us 0.379. Now that says that the sine of our second angle, theta 2, is going to be equal to 0.379, and then we get theta 2 is equal to the, remember, in order to solve this we have to take the arc sine of both sides. So that will be equal to 22.3 degrees. Now, I don't have decimals on my particular ruler here, but we can estimate that at, let's see, that'll be right, 22 right there. Okay. So that puts us at an angle of 22 degrees roughly. So this would be what it looks like. So you can see here, actually, that our theta 2 is a smaller angle than theta 1 because it's in a more dense material. Okay, this is basically the application of Snell's law, the law of refraction. I would like for you to notice that if we are to take a swimming pool, for instance, we can look at the case where we have light going into the pool and we have light going out of the pool. So let's do that real quick. Now here I have the surface of the water, so everything below that is water and everything above it is air. So let's go ahead and label that. And this time, instead of using 1 and 2, we can label them A and W for air and water. If we have a ray coming into the surface of the water here, we do the same process that we did before. This time, let's take it at, well, I guess let's use our ruler so we'll know what angle it is. So we can say this one is going to come in at, now that's 90 degrees. So what we're interested in is the angle with respect to 90 degrees. We're not interested in the angle with the surface of the water, which is the angle that's provided by this software. So it doesn't know that that's what we're trying to do. Let's go ahead and draw our normal before the ray hits. Usually I like to draw it after the ray hits. And I'm going to go ahead and draw a normal over here as well, because we're going to do a second exercise in a moment. So the first thing that we're going to do is have our ray come in at, let's say, about 32 degrees, something like that. So in order for that to be 32 degrees, 60 degrees with respect to the horizontal is going to be 30 degrees with respect to our normal, or the vertical. So I need to go a couple of degrees more than that. And I have a 58 degree angle with respect to the horizontal, which means that I have a 32 degree angle with respect to my normal, and I know that because the sum of them is 90 degrees. Okay, I bring my ray of light in. It strikes the surface at that point. We're interested in what direction this is going to go. We know that the index of refraction for water is 1.33 or 1.34 depending on which table you look in. It also depends on temperature of water and all that. And the index of refraction of air, of course, is just 1. So we're going to take our angle here as the angle in air, and our next angle will be the one in water. So we can easily solve for this. We have 32 degrees, so we can say here index of refraction of water times the sine of the angle in the water will be equal to the index of refraction in air times the sine of the angle in air. And we solve for the angle in water is what we're looking for. So we need to separate sine of theta in water. That gives us the index of refraction in air over the index of refraction in water times the sine of the angle in air. And then that gets us one step closer. I did this a little bit differently than I did in the last problem because last time I put a bunch of numbers in, but it can be also done this way. We take the arc sine of both sides to find theta in water, and that means we're taking the arc sine of everything on this side, right? So we're going to take the arc sine of, make sure that this fraction is inside your arc sine, not outside. Sine of the angle in air, and that's just going to be arc sine of index of refraction of air is 1, index of refraction of water 1.33, and then sine of 32 degrees, full close. Okay, and that equals 23.5 degrees. Also a little bit hard to put on an integer ruler, but you know, I'll at least give you a sense of let's put our pivot point right there. I'll at least give you a sense of where it's going. We want to go 23 degrees off of the 90-degree angle here. So we go 10 degrees, and then we go 20 degrees, and then an extra 3 degrees. There we go. Okay. So that would look like this. Now we check with our logic. We look at this and say, does it make sense that this angle would look like this? Well, water is more dense than air, and this angle is a little bit tighter than the angle outside. So yeah, that makes sense. That's reasonable. I want to try a new thing here where we have like a laser pointer that shines out of the water, and we want to shine out of the water at 23.5 degrees. So if we go about that process at this new angle here, at 23.5 degrees, I'm going to go ahead and draw it at that same 67-degree angle, because like I said, I don't have a 66.5 degree angle. I have to draw it at whatever integer I'm given. But we'll go ahead and claim that this is 23.5 degrees, and then we're interested in what angle it's going to leave the water at. So notice that there's something very interesting about Snell's law here. If we start off with this on the left side of the equation and solve for this angle, with this on the right side of the equation, and we're still solving for this angle, this math doesn't care or know whether the ray of light is entering the water or leaving the water. All it knows is that one side is going to be... This math doesn't know whether our ray is entering the water or leaving the water. All it knows is what it looks like on one side and what it looks like on the other. So if we had our ray of light coming in at this angle, then we can solve for this backward, and if we insert 23.5 degrees in here, we should get the same angle we started with on the way out. In other words, we're just undoing everything with this math that we did in our first equation. And you're welcome to run through that if you like, but the concept is that if you use this to solve for that, and you keep all your values the same, and then you come back and solve this for that, you should get out the other side that same 32-degree angle. So then we can take this and pivot it at 23 to 23 degrees, 32 degrees, excuse me, which should be right here. Okay. Okay, so this is the general principle behind Snell's law. There's all kinds of other, interesting effects that can come out of this. I think everybody is kind of familiar with the Pink Floyd effect. So what I want to do really quickly is look at the idea behind geometry and how we have to use, this is the hardest part about this, is using geometry to figure things out and trying to kind of find angles and proofs. Okay, so let's do that real quick. So I want to take an equilateral triangle, and this means that each of these angles is 60 degrees. And I'd like to claim that this is an object with an index of refraction of 1.7, and so it's some kind of dense glass, like fused glass or something, with an index of refraction of 1.7. And I'd like to shine a ray of light into this thing at a 40-degree angle with respect to the horizontal. So how we would picture that is we would take our ruler and to make sure that you can, as you can see, that it's 40 degrees with respect to where we started, which was the horizontal on this particular ruler. So I know that if I draw my ray up to this surface, that what I'm measuring with respect to is the horizontal. And it's important for us to get those things straight before we apply Snell's law in this case. Now, what is the first thing that we do? Every time we draw a ray of light, we always have to draw our normal. So let's do that real quick. Our normal triangle is at 60 degrees, then that means that we should be at 30 degrees here in order to make sure that this is 90 degrees. So this would be 30 degrees here. This angle here would be 30. This is 60, and therefore this is 90 because they all have to equal 180. So that's one of our features of triangles, right? So we draw our normal to the surface because that's always rule number one, right? Now it doesn't hurt to go ahead and also draw our horizontal so that we have a concept of what we're actually trying to achieve. There's the horizontal. I'm going to draw this a little bit lighter, so just a little lighter so that we don't get all of our lines confused here, okay? So now we can actually start looking at, look at all these angles. There's so many angles here, so we have to be very careful about which ones we're interested in, okay? If this is coming in at 40 degrees with respect to the horizontal, my first question, if I'm going to write down Snell's law, which I am, Snell's law is given as the index of refraction of air, sine of the angle in air with respect to the normal, is equal to the index of refraction in glass, sine of the angle of the ray of light in glass with respect to the normal. So I'm interested in the angle outside with respect to the normal and the angle inside with respect to the normal, right? I already have my two indices of refraction. Glass is going to be 1.7 and the other one is air, which is just always 1. If we have, if we write this out, we get that angle right there. Can we determine what that is? We know that this angle right here is 40 degrees, right? And we know that this angle, according to the triangle that we just created, was 30 degrees. And so the total angle here, which is given by theta A, theta in air, the angle of our ray with respect to the normal in the air side of the interface, theta air, is going to be equal to 40 degrees plus our 30 degrees, so it is 70 degrees with respect to the normal. That's the one we're interested in. Let's go ahead and label that there, okay? So then what we do is say, if we wanted to know what direction this thing is going to go, we have to keep in mind that the direction the ray is going to go is with respect to the normal inside the glass. We can now solve for that mathematically. We go through our same process here. The sine of the angle inside the glass is going to be equal to index of refraction of air over the index of refraction of glass times the sine of the angle in air. And again, we can just take the arc sine of both sides for that final angle. Now I'd like you to note that if you run into an error in your calculator, it means you've done something wrong on this one. Later in the next video, we're going to show what happens when you run into an error on the calculator and it's meaningful. So we'll check that out. But okay, so here we get theta glass is equal to the arc sine of, and in this case we get 1 over 1.7 sine of 70 degrees. So this should be significantly affected. 33.6 degrees. Now don't jump onto your diagram immediately with this angle. We have to stop and think about what that means, right? So let's go ahead and put our ruler up, and remember that we have a horizontal here. We are interested in the normal, which is at 30 degrees, and the angle with respect to the normal is going to be 33.6 degrees. Now keep in mind what that means is that as this ray is heading in that direction, it is going to be redirected toward the normal, closer to the normal, right? But how much? So we're interested in, as a matter of fact, this angle, right? So we need to know how far that's going to go. It's going to go 33.6 degrees. So we're going to go 30 degrees and then an extra 3 degrees, 0.6, which I don't have a 0.6, but I'll do 4 degrees, which means it's going to go this way. Okay. Now, in this question, I may actually be asking, so this is theta in glass, and then I might actually ask, hey, what happens to that ray in the next interface? And if I do, then what you have to do is take that all the way up to the interface here and begin an entirely new problem. So what I might need to do here is change colors so that I can keep in mind that I now have a new ray. I'm going to be taking this ray, and now I'm going to be interested in how it bends when it gets to this next surface. So the first thing that you're going to need to do is draw the normal to your surface, and so with our ruler we can take this and move it to 30 degrees, and what that does is ensures that this is exactly 90 degrees from this other 60 degree surface. Now how did I know that was 30 degrees? Again, if this is 90 degrees here, I'm making a triangle here, temporary triangle here, and if this is 90 degrees and this is 60 degrees, then that must be 30 degrees with respect to the horizontal. So when I have 30 degrees, well, that means that I have the correct normal. You can also visually inspect that that normal makes sense. So there's our normal. We have a new angle that we need to consider, this angle. And that angle I might go ahead and call theta 3. And then I'm going to have theta 4 when it comes out of the glass. Let's go ahead and tilt this to where this was. Remember that we were originally headed in this direction here, but we are not going to continue going in that direction, and intuitively you should see we are also not going to be bending toward the normal here because we're going from more dense to less dense, so that means that we're going to be bending away from the normal. Okay, so we would expect it then to do something more like this. Okay, let's take a look at that. What do we expect? Well, we still have index of refraction 1.7 inside. Let's redo our Snell's law, but this time we'll say n3 sine of angle inside the glass, or 3, is going to be equal to n4 sine of the angle outside the glass, 4 on this next transition outside the glass. So we're now interested, in this angle here, right? So we find theta 4 again through that same process. This will be the arc sine of, and go through this algebra carefully. I've just done it too many times, so it's not a terrible process for me to do in my mind. Okay, so we did the same process we did up there, but this time we're just doing it in reverse. We're not going to end up with the same answer this time because our ray is not entering at an angle that is with respect to the same normal that it was before. It's elevated a little. It's a little bit tighter of an angle than it was here when it was going into the glass, right? Now what is that angle? Well, this is the hard part. So let's take stock of everything that we have here. We know that this one was at 33.6 degrees with respect to the horizontal, and we know that the normal is at 30 degrees with respect to the horizontal. So that means that if we had our horizontal here, that would be 30 degrees from the normal, but instead we are 3.6 degrees in from the normal, which means that theta 3 is given as 30 degrees minus 3.6 degrees. So that gives us 26.4 degrees. So our theta 3 is actually 26.4 degrees from the normal. And not from the horizontal, right? Now, if we double check our logic here, you can see that the angle is actually at like 3 degrees here, or if I pull it up a little bit too far, it's at 4 degrees. So yeah, so we're at about 3.6 degrees from the horizontal, right? And so we would be then here is 0 degrees, and we'd go 3.6, and then the rest of the way would lead us to 30, right? So that's the logic that we use, or the mathematics that we use for this geometric proof. Well, okay, now that we have that, then all we have to do is plug in our numbers. With N3, the index of refraction 3 is equal to 1.7, and N4, the index of refraction 4, is the index of refraction of air. And so that would result in an angle of 49 degrees with respect to the normal. So we are going to take our, this one is at 30 degrees, so if we wanted to go this way and make sure that we're exiting on the downside of the normal, because we came in on the upside of the normal. So this thing is going to be bent outward, right? By how much? Well, it's going to be 49 degrees from the normal, so we go down by 30 degrees to get to the horizontal, and we still have an extra 19 degrees more to go to get 49 full degrees from the normal. So in other words, this normal is at 30 degrees one way from the horizontal, and then our refracted angle is 19 degrees the other way from the horizontal. Okay. So let's go ahead and draw that ray outward like this. And you can describe this any number of ways. You could describe this as 19 degrees with respect to the horizontal. You could describe it as 19 degrees with respect to the floor. But ultimately, this is the direction that this thing is going to come out of glass. Okay. So I know that this is like about the trickiest that you're going to get, is this kind of problem where you really have to think very carefully through each of these angles. And I do encourage you to go back through this segment of the video to make sure that you understand where all of the angle proofs are, because you can use all manner of different angle proofs. You don't have to choose the ones that I mentioned. There's so many ways to prove what each of these angles is, but we wouldn't obviously have enough time to go through all of them. So. Okay, in the next video we're going to study what happens when we get light coming out of a surface at too high of an angle,